Hey guys, welcome. My name is Fori, and today we're going to be examining how to draw different types of molecules and compounds. Now, if you are a fan of these videos and you'd like to see more, please ensure that you leave comments in our section regarding what sort of things you'd like to see, whether it's you want an explanation on how taxonomy works, or you want to understand the basic laws of motion, or you want to look at electricity. Any suggestions that you have are welcome, and please ensure that you click like and subscribe, and also follow us on Instagram and other forms of social media. So, getting back to today's problem. Chemicals are a little bit difficult to understand at first because there's something a little bit abstract. For instance, I can tell that certain materials are made out of plastic or certain metals because I can touch them, I can feel them, I can interact with them, I can test them in different ways. But when we're looking at the actual structure of molecules and compounds, it gets a little bit trickier because you can't actually see them. So, today, we're going to start basic. Now imagine that you have this information in front of you. Oh, there we go. So for the most part, when you start off with basic chemistry in years 8 or 9 or 10, you start using this information. Now, the chemical formula and the structural formula are two very important pieces of information because they show us A, what elements are involved in making that compound, and B, how they're put together. You know for a fact that if you have Lego pieces, you can take it apart and rebuild it using the same components. So, let's say you're looking at the chemical formula up the top. The chemical formula just shows the elements and how many there are. So in here, I can see that a lot of them involve nitrogen, oxygen, carbon, and only one of them involves chlorine. To write the first letter, you use a capital. When you're doing the second letter of the same element, you always use lowercase. So that's why it is not a capital L at the very end, because it's part of chlorine. If it was a capital L, I would assume that's a different element entirely. Now, these four are pretty common compounds that you will use a lot, particularly if you start doing chemistry in years 11 and 12. So we have water, or dihydrogen monoxide. Di meaning two, hydrogen, mon meaning one, oxygen, so two hydrogens and one oxygen. I have oxygen gas, which is bonded together as O2. I have ethanol. Now, a lot of you might be thinking, why don't they just put this H at the end with the others? It's because this OH group at the end is typically what we call a functional group, and you're going to cover that in year 11, okay? Functional groups are sort of like a unique property of that compound that allows it to do certain things. Much like how if I gave you rappelling gear, it would mean that you could feasibly abseil or rock climb. Without it, you can't. Hydrochloric acid here. Now, below that, we have their structural formulas. Structural formula is an image of showing how they are connected. So if you see the picture, we have the same four compounds. So we have water down here where the oxygen is binding the two hydrogens together to it to make it look like a boomerang sort of shape. Over here we have the oxygen gas. Each dash represents a pair of electrons that are bonded together somehow. So over here, between the hydrogen and the oxygen, you have only one line, indicating that it is a single bond. Over here, we have two lines, indicating that it's a pair of two electrons. So 4 electrons total, creating 2 bonds between them. Down the bottom here, we can see ethanol has a lot of single bonds connecting these hydrogens to these central carbons. And at the very end, that functional group that I talked about has a weird sort of shape that's reminiscent of water. If you've ever heard of the word ethanol, you know for a fact that it can mix with water. Hence the reason if you buy alcohol from a bottler or a liquor store, you know for a fact that there's not a layer of water and a layer of alcohol. It's all mixed together. That means that these compounds have to be able to interact. Now over here, the hydrogen and chlorine are bonded together through what's known as an ionic bond. This is different to the others, which all involve non-metals. These are held together with covalent bonds. Now, we're going to touch on that a little bit later on in a later video, but for today, these are the two formats that you are going to use when you are drawing or you're explaining how a compound operates or used in a chemical reaction. Okay? Now, let's say you want to go a little bit further. You want to impress some people by showing them exactly what's happening. Well, You can do that using a Lewis structure. Now, each of these dashes that we've talked about is representing two electrons that are held together. So they hold their atoms together respectively. Here, the other little dots that you can see are the other atoms or other electrons that aren't forming a bond. So let's say we're having a look at water. We know that in its valence shell, so its outermost shell of electrons, water, or oxygen, has only 6. It wants to get 8. Okay, as part of its octet rule. It wants a full outer shell. Now, is it easier to collect 2 electrons to get that full 8, or get rid of the 6? If you answered 2 electrons, you're correct. So, by sharing its electrons with hydrogen, oxygen can claim it has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Also, hydrogen can claim that it has 2. Hydrogen is a very small atom. It only wants 2 in its outer shell. So 1, 2, or 1, 2. It's happy as well. Now, if we're looking at ethanol, the reason why we have this weird sort of dogleg shape at the very end is because all the electrons are centered on one side of the oxygen. This is actually a pretty common concept. It's the reason why water is able to dissolve substances like salt, and it gets larger when you freeze it. So when we have water, up the top here, these two hydrogens don't see a lot of their electrons. I mean, they do. They can claim that they have 2 electrons and they're happy, but that they don't have a lot to do with it because they don't have the charge to pull the electrons back towards them. It's much like how if you're working in a team, one person is always going to claim, or one person may claim a lot of the credit for the work that's done by a lot of your teammates. Your teammates might not speak up. So the oxygen, the person who's claiming all the work, has claimed all these electrons. They've kept them mainly for themselves. The other teammates who don't speak up are like the hydrogens. So in this case, since electrons are negatively charged, hydrogen becomes like a positive end of a magnet. Oxygen becomes like a negative end of a magnet, and they attract each other as such. And because of that, they create all sorts of weird shapes like snowflakes. Water is one of the few substances that expands and gets bigger when it's frozen solid. It gets less dense. That's why ice floats on top of water instead of sinking underneath it. And down here, we can see that these oxygens are working together to get 8. They're bonded to each other. So we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, same with the other side. They're both claiming to have 8. Over here, we have chlorine and hydrogen. Chlorine is a much more extreme version. It hoards electrons because it's so close to getting that 8. In its natural state, it only has 7. So 1, 2, 3, 4, 5, 6, 7, 8. It's happy. It's not going to let go of that electron as long as it lives. Okay? Now, Lewis structure is useful particularly if you want to look at how ions form. So how differences in electron number can alter the natural state of an atom. But let's say you want to go a different direction. Now, if you're doing chemistry with a model kit, you know for a fact that you can get different colored balls that can connect together with the little gray stubs. This is what we call a ball and stick model. Ball and stick models are very useful if you're color coding something. So say, for instance, I want to draw a super massive compound. Okay, it's going to take up most of my page. Now, if I'm doing this, the detail that I'm going to have to include has to be uniform throughout. So if I include elements for one part, I have to include elements for all of it. It'd be easier if I can color code it and then include a key on the left-hand side. Well, my left, your right. Now, that's easy enough. You can build that and you can manipulate a three-dimensional model. Ball and stick is a very simple concept that we use to try and illustrate an idea in our heads. However, an actual atom is more akin to the space-filling model. See, electrons, they're moving at such high speeds, we don't know exactly where they are at any given time. So, if I have these merged colors together, then odds are that means that where the merged portion is, it's where the higher electron density is, okay? So it's much like how if you watch a tracker over a given period of time of someone, you can work out where they live because they keep going back to that same point, okay? That's where the house is. Now, all of these different types of models, from ball and stick, to your space filling, to your Lewis, to your structural, to your chemical, all of them can be used, but they're all used for specific purposes. If you are in 7th grade or year 7 through to year 10 or 10th grade, odds are you're more likely going to be using structural, you're going to be using ball and stick, you're going to be using chemical. Okay, structural, ball and stick, and chemical are going to be your 3 best friends. If you decide to go into chemistry, you're going to have to become familiar with the other models and why they work. Okay, so that's it for today's lesson. Please ensure that you like this video if you did enjoy it, or leave some feedback on what sort of things you would want to see in the future. Would it be, I need help writing a report, or I need help performing this experiment, I need help designing an experiment. Okay, all of these things I'm much more than willing to help with. But as always, I've been Forry, you've been amazing. I'll see you around.